Very good morning, afternoon, or evening, depending on where you are. It's my pleasure to introduce Professor Fabrizio Granelli, Professor of Department of Information Engineering and Computer Science at University of Trento. And he is one of the experts in 5G and 6G communications. And my interaction with him started with UAV communication standards, and particularly if you look at the historical background, recently rather, it's not that old, but we started 1920.1. Probably this is the very first standard in communications or UAV communications. And then we have 1920.2, and now Fabrizio is chairing 1954. This is agile and more intelligent UAV communications. So it deals with ad hoc networking of drones in a much more agile way. So without much ado, I would like to request Professor Granelli to give his presentation on UAV communication standards. I hope you will enjoy. Thank you so much.
Thank you very much, Ganesh, and thanks for VTS for inviting me today for the presentation. So as Ganesh introduced, my presentation will be on communication standards for UAV. So first of all, if you want to reach me after the presentation, or if you're interested to interact with me, please feel free to use my email address that you can see in this slide. I will be happy to interact with you even offline. Let's just see the outline for today. So I will just briefly provide the motivation why this topic is important. I think all the people that are attending for sure already know why UAVs are so important today and so relevant. However, I will try to go very fast into UAV communication requirements, since I would like to present which are the specificities of UAVs and why communications are very important, which are the constraints or the KPIs that are required to be satisfied for UAV communications. This is because the following part, which will be communication standards for UAV, is a part that, as Ganesh mentioned, it's really live because we don't have a definite solution right now, but we have several parts of the puzzle. And what I would like to point to is to some standards that I believe will be relevant today and in the future for UAV to communicate properly. And finally, I would like to outline some future directions and some conclusions about this topic. So we all know why UAVs are important, because they have a lot of interdisciplinary applications that go from traffic to environment, for example, because we can use UAV for checking pollution, or especially in emergency services, they are very popular for firefighters, for first responders, but also in other kind of business. For example, there's a lot of applications on package delivery and monitoring, for example, critical infrastructures. And in general, UAVs are impacting society because they are a part somehow of the digital transformation of society, of the next step of automation in society somehow. So in this framework, we are in front of a technology that it's already tangible, but it still has a lot of challenges because it's a technology that went very fast to the market. However, it still suffers from constraints because there are some economical constraints because of the battery costs, the capital cost to be involved in building a swarm of drones, for example. The fact that drones are operating in 3D space, so they are subject to adverse weather conditions. And one of the main points that we will also address today is the fact that drones are airborne devices. So they require air traffic management, which is something that, of course, increases the complexity in the communication and needs to involve drones in a lot of other communication scenarios besides just controlling them, for example. there is also other impacts of the drones that require further regulation, like frequency of utilization for communications, but also altitude, flying altitude, regulation about how to drive them, who can do it, which kind of automation is possible, and so on. So it's a technology that is live. And today we will focus on the UAV communication in particular. Communications are at the heart of practically all applications of drones, because we need either to control the drone from a person, so a pilot want to control a drone, or the drone can be self-piloting, but it still requires to be awareness of what's happening around. So there is always some sort of communications. And the communication requirements for UAVs are, of course, a level of agility, like Kamesh was mentioning, and at least the possibility to self-organize communications. So there are people speaking about ad hoc networks in the sky, but it's important that drones are capable of discovering the neighbors, form networks when it's necessary, but also simply interact with the infrastructure or other drones when they are path planning or generating routes for example, autonomous navigation. And one of the standards that started to work on UAV center communications is P1920, that is chaired by Professor Kamesh Namuduri. That was the first standard that addressed the problem of understanding which are the data that we need to exchange and how we should exchange data, mostly on direct links for the time being. And one of the biggest problems is, as usual, spectrum utilization, because today, a lot of UAV devices that we find on the market, I'm speaking in this presentation, by the way, mostly of civil drones, civil UAVs, operate in the ISM bands. So a lot of them operate in shared bands. And for this, there is the need to still guarantee a given quality of service in the communication, because we want reliability, we want low latency, for example, and so on. So it's a challenge to understand how we manage the spectrum resources themselves. And for sure, what will happen is in the future, there will be one of these three solutions for sharing the spectrum with other technologies. For example, there is opportunistic spectrum access, where UAVs are secondary unlicensed users that use the gaps or the white spaces left from licensed user. There is competitive spectrum access, where the UAVs, in this case, that are unlicensed users, can place bids for getting spectrum access from other sellers that already own a part of the spectrum. But there is also cooperative spectrum access, for example, where the primary users, for example, the cellular network, provides spectrum to the UAVs in exchange for other advantages. For example, to use UAVs also as relays or to improve communication quality. So this part will be probably subject to different regulations and hopefully good solutions in the integration with existing technologies. And in general, we need also ad hoc communication protocols, because we need protocols suitable for exchanging data that UAVs require. So a little bit of which might be communication requirements. Here I try to simplify, because of course they depend a lot on the scenario that we want to address, but the main relevant, in my opinion, are the so-called C2 communication requirements that allow to control flight operation. So this means that the drone typically has a link either to the pilot, so the person in charge of driving the drone, if it is in proximity or in a range where communication is possible, because for example, the pilot can drive with the stick and steer the drone and position it and do the job remotely, while remaining typically in line of sight. But there are also other applications that, even though have automatic flight characteristics, they still require interaction with, for example, the UTM, which is the traffic management system that the drones should use for avoiding obstacles and also understanding how to interact with other kind of air traffic. And in this case, I took a table that is taken actually from a document by 3GPP. So those are the requirements that 3GPP used to define some parts of the standard, where you can see that the requirements run from very challenging requirements like 40 milliseconds in the case of direct control of drones, and mandatory acknowledgement, for example, so we need reliable communications, down to more, let's say, less requiring constraints, like, for example, when we connect to the autonomous navigation infrastructure, we can tolerate up to half a second of delay, and we can also, let's say, accept some variations around that number. So there is a way to specify, depending on which kind of drone we have, automated or non-automated, which are the corresponding requirements. But there are also other kind of communication requirements that are related to security, for example. This is a very big problem. And today I will focus mostly on the communication themselves, but we have always to remember that we need to be sure that drone communication is safe, especially wherever the drone navigation is implied, because every time we want either to control a drone or to provide drone with information that is useful for the navigation, we must be sure to avoid attacks like replay attacks, jamming attacks, for example, that might be a serious problem, but also data tampering or impersonation. We can have a false, let's say, drone or a false pilot to interact with the drone. So whatever technology we will define in terms of, let's say, physical communication performance, we need to embed in the standard also security requirements. And the setup of the network in drones is extremely diverse, because it depends how we consider the drone and how we want to integrate it with existing infrastructure. Because in simple examples, we can use UAVs as sensors, like you see in the middle of this figure. So in this case, we use UAVs as movable sensors. So somehow they have simple requirements for networking, but when we are in presence of a mobile network infrastructure, like you see in the right part, there are situations in which maybe we would like to use the drone as an aerial relay for improving the communication in a specific range. Or in the left part of this diagram, you see also one of the typical emergency scenarios where maybe there is no infrastructure and we want the drone to be an aerial base station capable of providing uplink and downlink communication in a specific area. So those are, let's say, sort of single op or simple multi-op communications. But we also have more complex situations, like we can build a single layer line of sight communication among several drones in a swarm. This can be done without infrastructure, or it can be done also in presence of the infrastructure, like you see in the middle of this diagram, where we have non-line of sight communication also to build a network of drones. And we can even arrive to situations like the one on the right, where we have a swarm of drones that are interconnecting using a multi-layer architecture. That, of course, depends on the scenario that we have, on the environment, but also on the application that we want to deploy. However, the fact that drones move in the 3D space generates an unprecedented, let's say, sort of mobility pattern that typically is really challenging for the infrastructure that we have, because infrastructures for communications are typically built for vehicles on the ground or people on the ground, or buildings, for example. So they are not appropriate in general to cover areas where the drones might fly, like at relatively high altitude, like 500 meters and so on. So even if we have standards that potentially can interconnect the drones, we need to have specific versions or specific refinements of those standards in order just to implement a suitable way for drones to communicate. Then we can see also, once we can connect those drones, what they can do more, because they are not simply end nodes, but as mentioned also in the previous slide, they can be part of the infrastructure of communication. And I will speak about that a little bit later on in the presentation. One important aspect that I would like to include among the UAV communication requirements is the fact that there is the need, clearly, because a lot of applications tend to push towards autonomous operation, we need to have an architecture for a traffic manager. So this is an example. I took the NASA UTM architecture, the Universal Traffic Management Architecture, just to show you that already this piece of the puzzle, because this is intended only to cover a way for UAVs to be aware and to get information and commands in order to satisfy let's say, the safety also of the aerial space. Also here, we already have a complexity because, as you see in this case, we have a diagram that I don't go in the detail, but it already shows that we have the interaction and communication already among different actors. Like the green part is for the operator of the drones, so we can have a way, or even if it's autonomous, the drone will have some operation center to control the drone and to provide missions for the drone. We have external stakeholders, like stakeholders for public safety, or even public bodies or companies that offer services to drones. And we have, also, of course, a flight information management system, at least, that will be the one that define how to manage the airspace. Typically will be probably governmental or in some way territorial based, but this will be the part that will provide the regulations and it will need to enforce those regulations to the drones. So you see the main interaction here is between the flight information management system and the UAS service supplier. So you see that is this interaction where there are constraints and directives that needs to be provided to the UAV operators and path planner and mission planners in order to satisfy the regulations and to maintain safety in the air. And this, of course, we require to use some sort of infrastructure itself, even before going to the UAVs that are here, these UAS, so unmanned aerial systems on the bottom of this figure. So you see there is a lot of other communication involved. We will not go into details, but some parts of this information will be conveyed, needs to be conveyed to the UAVs too. So somehow we can see UAVs as end devices. Here I'm just quoting, if you're interested, a nice paper that is publicly available about some applications of UAVs. In this case, for example, if we think to use UAVs in a city, we can use a mobile network. That will be one of the standards that I will outline a little bit later on, that can handle UAVs as generic end devices, because typically this will fly not a very high altitude. So they can handle UAV generated payload, like for example, video or sensor data, like they do for mobile phones. And there is also the opportunity to handle beyond visual line of sight communications. So for example, I might think to drive my own drone through the mobile network. That, of course, is a new sort of marketing scenario for 5G or 6G networks. This would be useful because if we think about USB as end devices, we can reuse existing infrastructures. So There are standards that are already solid and reliable, like 4G, 5G standards, that are already covering a lot of territory that we might reuse, but of course, those need to be tuned to accommodate the UAV requirements. So we have networks that we can use, and we are definitely able to use them today, but we need also the capability of the network to be tuned for those kind of applications that are a little different from the considered, let's say, smartphone or maybe last mile applications that are today in the mind of mobile operators. One thing that is important in UAVs is the concept of UAV corridors. So we will need, and in several countries, we already have some sort of standards, at least we have constraints about where drones or UAVs can fly. Because UAVs are objects that might be dangerous in the wrong place. So what we expect is that around the world, maybe with different flavors, but there will be some so-called UAV corridors that will be regulated by the different governments in order to provide rules about where the drones can fly. For example, the maximum altitude that typically is around 500 meters, the fact that for usual operation, the UAVs should not maybe go on top of the people or very nearby to citizen, and so on and so forth. But this also means that we need to be able to control very well the behavior of UAVs. And again, we must make UAVs self-aware and aware of the context they are operating in. So this means that if we connect UAVs to ground networks, then we need the ground networks to be able to provide a specific support for the KPIs that are required for drones communication. So somehow we need to rethink how to design ground networks and how to operate them in order to support and integrate UAV communications. In this framework, there is, of course, let's say the two technologies, and even merging them somehow, because one possible technology is to use vehicle-to-infrastructure communication. For example, vehicle-to-infrastructure might be using 5G mobile networks or maybe 6G to interconnect UAVs to other services like the traffic monitoring or traffic management service, or to interconnect between themselves like we do with smartphones and services today. And also we have vehicle-to-vehicle. Vehicle-to-vehicle is important because any mobile infrastructure does not cover 100% of the territory. So we will still have holes, even if we use mobile communication standards like cellular networks. And for this reason, we need always to think that drones might resort to vehicle-to-vehicle communication. So they might use the capabilities to connect to neighboring drones or to other aerial platforms in order to extend their possibility of operation. And in this framework, there is not much solutions. Maybe we can reuse some vehicular communication standards like 802.11p or the extensions, so the Wi-Fi, let's say, for car-to-car communication. But as Kamesh mentioned before, we started a specific standardization group that is called 1954 in order to explore the possibilities of achieving a spectrum agile communication in the vehicle-to-vehicle scenario, so that we can allow drones themselves to become aware of the neighbors by interacting with them through communications. This is a standard that we are going to develop in the near future. If you are interested, please check out the link on the bottom of this slide. So, which are the solutions that we have today? Because today drones still exist, they are being used, they are very popular, and they already communicate. So what's happening in the technology, what's happening today, and what is going to happen in the near future? Here is a list of how we can think to enable drones to communicate effectively. Of course, the direct links, so we can have the possibility to have direct communication between pilots and drones, or drones and drones if we want, or drones and infrastructure, so to have a direct connection somehow. We can use satellites. The benefit of satellites is, of course, they are covering a very large area, so they are a simple to deploy communication infrastructure. We can think about flying ad hoc and mesh networks, so we can have swarms of aerial vehicles that communicate among themselves to bring services. We can think about, again, cellular networks, and there is people that also proposed the concept of the Internet of Drones. So I will go through these points in the part in the second part of the presentation, in order to outline which are interesting points or relevant documents that you might want to go more in details. Of course, in a short time, it's not possible to provide you all the technicalities, but I hope that with this presentation, I will be able to point you to some relevant documents, some relevant parts of the standards or working groups that you might want to check to get for more details, or maybe even participate in their activities. So, as I said, the simple is direct link communication, and maybe the more mature somehow, because that is the basics. If we don't allow the drone to be able to self-navigate, so to be autonomous, for sure we need interaction with the pilot, with the controller, and this typically happened in the ISM band. So typically with controllers that operate at 2.4 gigahertz, which provide some 100 meters of coverage. In this case, typically the communication is limited to line of sight. So when we think about direct link, it means that the drone and the other communication node, be it the pilot or something else, they are in line of sight, so the communication can happen in straight line, let's say. There is different technologies available. Here I wanted just to open a parenthesis about the existence of this MAVLink, that is a de facto standard for providing messaging support to drones. Actually, this is not a low-level communication standard, so it's not a standard that operates at modulation or MAC level, let's say, if you are if you think about the TCP/IP stack, but this is a protocol that mostly operates, let's say, in the application layer of drones. So this standard is irrelevant because is a lightweight messaging protocol that allows to exchange information between typically the drones and the controller, or even between onboard components. And I use this because I wanted to outline that even if though it's a simple protocol, it's still quite sophisticated because it allows you to have both publish subscribe solutions. For example, you can have autopilot data streams that are used to provide information about what's happening in the flight, just for, let's say, recording flight information, but also point-to-point communications that are usually employed in case of data streams that are subject to delay constraints, for example, for directly controlling the drones. And also, everything is in XML. Here, I just took the one example about how flexible this protocol is, because it operates in the application layer. So we are experiencing solutions where the MAVLink is used on top of the TCP/IP stack, as you see on the right part. So this allows to use, for example, Wi-Fi or any other technology to transport the data, but it's also possible to use MAVLink directly on the serial interface. So that is a way, for example, to transmit data on board, or even to use simpler applications, simpler communication protocols that operate in a serial manner. When we consider the introduction of satellites, there are already some, let's say, at least spectrum assignment, because in the World Radio Congress of some years ago, in 2015, they specified the possibility to use Ku, Ka bands for UAV to satellite communication. This is good and profitable in case of beyond line of sight or large distance communication, because satellites typically cover a large area of the ground, of the terrestrial part of Earth. So it can be a very suitable standard for providing a link to the drones. And it works very well because it does not require several handovers like maybe a mobile network. However, we have disadvantages because in this case, propagation time might become very large, typically up to half a second, which already does not allow to have, for example, remote operation, direct remote operation. The payload has a problem because drones are lightweight typically, so to have a satellite antenna requires a large space and a large weight to be supported. And also satellite communication are affected by weather conditions. This is actually a problem of drones in general, because they have problems when it rains, because they are in the environment itself. So they are subject to all weather problems, but especially in the case of satellite communication. So another solution might be to be more local and to adopt ad hoc or mesh networking, so to allow drones to build a self-organized infrastructureless network that can be built on top of Wi-Fi or WiMAX technology, for example. There is already the concept of FANETs, so flying ad hoc networks, that allows to deploy the communications and connectivity in a very flexible manner and with very low cost. However, ad hoc technologies at the moment are still subject to problems of reliability. So to be able to cover an area and provide reliable connectivity, to support mobility. In the case of drones, this is becoming extremely complicated because drones can move very fast, and of course the topology control becomes extremely tricky. So to maintain the connectivity is not simple today, and in general it requires further operation, because a lot of mesh networks today are based on limited mobility, and in the case of drones, of course, we are going towards instead the other extreme, let's say, of the mobility pattern. The most probably mature technology is, besides direct links, the cellular supported UAV communications. So to enable communication using cellular mobile networks, the thing is, we have the availability of the licensed spectrum, because 4G, 5G, 6G will have dedicated spectrum bands. So we reduce the problems of sharing the bandwidth with other standards, because somehow UAVs can be client of the cellular infrastructure. So at the end, it will be the cellular infrastructure that will interconnect the UAV to the ground station or to the UAV pilot in a reliable manner. Mobile networks are mature today to provide high throughput, relatively low latency and reliability. So somehow it's simple to think about UAVs as clients, but it's also important to think about UAVs as part of the cellular infrastructure. I will spend a few minutes later on. This means that we might think also of UAVs as ways to extend mobile networks by integrating UAVs in their infrastructure as aerial base stations or flying relays. And as you will see now, I will go through a few points of work that is happening in the 5G standard. You will see that also this scenario is starting to become interesting also for the 3GPP standards. I don't go in details, but there is a, let's say, not an extreme, but a very revolutionary concept of Internet of Drones. That means to use Internet technologies at the service of drones. So to rethink somehow or to reuse Internet technologies, but to build a suitable environment for drones-to-drone communication and drone-to-infrastructure communication. So the idea of Internet of Drones is to embed in the design drones management, flight control, resource optimization, and mission planning within the concept of the internet somehow. And mostly to integrate in this way the drones in the internet itself. There are already works on this where they introduce ad hoc networks concept in order to enable coordination among local UAVs, and also the idea of the zone service provider. So to use for communication of drones a part or all the backbone of an internet provider in order to provide a tunnel somehow to the ground station or to the pilot or to the mission planner. In case of 3GPP, we have, 3GPP is the standardization body behind 4G, 5G cellular networks. Already from release 15, which was the first one to start designing 5G, the 5G network, there were already studies on how to provide LTE support for aerial vehicles. So even though 4G was not very low in terms of latency that could provide, there was already working groups studying how to integrate in 5G signaling protocols for aerial user identification and to provide telemetry data of drones, as well as to use the mobile network for interaction with the traffic management system, with the UTM. This continued and was extended more in the next releases. To give you an idea, today, the release 16 is the last released version of 5G, and 18 is being developed at the moment. If you want, there is this survey that provides more information. However, to be short, in release 16, there was specific effort in UAV remote identification, because it's important also to understand how to identify UAVs and how to enable air traffic control, because of course, in order to make UAV technology viable, we need to guarantee that UAVs are constrained by traffic control commands like airplanes, helicopters, and other flying devices. But also there was work on tracking. So in order to help, let's say, to help reaching out the altitude of UAVs. That was a work that started in release 15 also, because in order to support UAVs, we need to have the capability of tilting the antennas, at least to be informed, the signal, in order to cover a larger area, because typically antennas are pointed to the ground. So there are these modifications that allow to increase the quality for the drone channel. And in the current version, let's say in release 17, they started the work on the key performance indicators. So they started to integrate among the 5G services the quality requirements for drone communication and service provisioning, and also they tried to understand how to integrate UAVs within the services and network exposure provided by the standalone core of 5G. Moreover, they are working at extending the requirements that were used for vehicle-to-X communications and mission-critical operations also to the case of the drones. In release 18, which is the one that is being under development, there are working groups that are working in signaling for UAVs, multicasting, and also how to use beam management techniques below 8 gigahertz in order to suitably cover the area covered by UAVs. An important aspect is that 5G introduced this idea of slicing the network, so to dedicate specific overlay networks for UAV communications. And of course, the straightforward question is, can we reuse at least one of those slices for drone operation? Because, for example, we have one dedicated slice in 5G that is for ultra reliable and low latency communication that fits very well with the drone operation constraints. In general, you know that 5G has a sort of flexible design through slicing so that we can support three main families of application: mobile broadband, critical communications, and machine-to-machine communications. These three kind of scenarios fit well drones because we have actually three typical families of traffic that might be generated or consumed by drones. And they are actually quite well mapped in these three situations because the mobile broadband scenario works well if we use UAVs as sensors. For example, we can have high definition video streaming to capture data from the drone. We can use massive machine-type communications to interact with, for example, the traffic management service. And we could use and reuse the ultra-reliable low latency patterns for controlling UAVs directly because of the low latency feature when we think about beyond visual line of sight scenarios. So one application of 5G might be directly to build network slices that are implementing these constraints, at least the yellow one, the one on critical communications, to integrate drones in their infrastructure as other services. However, the drones can be also used to build the network. And here I will very fast introduce the idea of Open RAN or Open vRAN, which means the possibility to split the functionalities of the base station in order to enable more flexible deployment of networks. And here, I tried to picture some examples. On the top, you have the radio frequency antenna and all the operations that bring to the MEC framing and so on. The concept of Open RAN is that you can split with using split A, B, C, D, and so on that are the red. And this means that you leave a part of the functionalities on the communication hardware, so near to the antenna, and another part can be put in a remote location, while satisfying some specific constraints. For example, if we split with split D, that is quite a popular split, we need to achieve at least a throughput of 180 megabits per second and the latency of some hundreds of microseconds, maybe some milliseconds in an extreme. We can exploit this actually in this scenario that we studied actually for bringing connectivity on Mars, but it can be used on Earth too, where we split the base station between a drone and some LEO satellites or even CubeSats. By splitting, as you see here we used split B, so that some functionalities of the base station are supported by the drone in proximity of the user, and they are moving to follow the user, and some parts can be deployed somewhere else, maybe in a satellite in orbit or in a LEO satellite. And these diagrams show that it is possible to achieve, let's say, roughly at least 10 megabits per second connectivity on a very limited bandwidth, at maintaining also quite a low packet loss in a flexible manner. So in this way, we can deploy a network where it's necessary, but providing the full service to the mobile users. In this case, we were thinking about Mars because there is no infrastructure and there will be the need for robots and humans when we will colonize the planet to have directly communications without being required to build everything from scratch from the beginning. So just to summarize and to close this presentation, there are still a lot of open challenges in communication. So I tried to provide you some information about where standards are going, but there are, of course, issues about the specific constraints of UAV communications. As you saw, there are different families of communication traffic that require different KPIs. Of course, UAVs will tend to be used in emergency public safety communication for sure, like they are being used. And in the future, probably they will provide even more services if they will be more integrated in mobile networks. However, the point is always to have the UAV traffic management to be capable of controlling the safety of drones operations. And this leads to challenges in vehicle-to-vehicle and vehicle-to-infrastructure communication that still require at least some more work of refinement and improvement. At the same time, there is this capability of drones to become autonomous. So the shift between human control to automation is something that is happening also within the networks today with 5G and 6G in the near future. So probably artificial intelligence and machine learning will come in the picture also in drones communications and in drones operation, because they will probably go along the way of the network evolution towards a full automation of communication and operation of drones on a large scale. With this, I would like to close my presentation to leave some time for questions. But before, I would like to thank the Vehicular Technology Society for sponsoring this event, the standardization working group that I'm working with, because I interacted with very nice people and they inspired me in some parts of this presentation. And then I would like to thank some colleagues that provided me material, suggestions that are mentioned here. With this, I close and leave you my email address. If you are interested, as Kamesh mentioned, I'm an expert also in the softwareization part. That is something that I believe fits well with the concept of drones. So if you like, here is one book that we wrote with some colleagues operating in mobile communications. And with this, I would open the floor to questions. So again, thank you very much.
Yeah, thank you so much, Fabrizio, for a wonderful presentation. It's a short summary. Obviously we have only 45 minutes to 1 hour, but it summarizes the state of art and the efforts, especially by VTS in promoting, in developing rather, and contributing to VTS IEEE standards is exceptionally covered. The floor is open for questions. I just want to make one comment before we accept questions. The 1954 standard is currently in progress. So if you are interested in joining and contributing, especially what we are doing in 1954 now under the leadership of Fabrizio, Dr. Fabrizio, we are looking at use cases, and then the how to make this network agile and spectrum agile actually, and then make it very reliable and intelligent. So please reach out to Professor Fabrizio or me to participate in these standards activities. So it's so let's now, you can, to ask a question, you can either put something in the chat or feel free to just speak out.
Yeah, there was a comment in the chat about also to consider 1609 family of standards. Sorry, I didn't write it actually in the slide, but it was included when I was speaking about, let's say, vehicular, more standard terrestrial vehicular communications. So for sure, it's welcome. Thank you for the suggestion. It fits perfectly. Maybe if someone wants to write in the chat some questions, if it's
yeah, no, yeah. Yeah, there is one more point here.
Okay, yes,
Split.
there is.
There is one question on chat.
Yeah, on split D latency. Yes, it's one way. It's a one-way latency. Yes, because just a short clarification, because I went very fast when I was showing this. That is typically the data here are one-way latency, because the standard, the 5G standard specifies a specific timing between, for example, demodulating and applying the turbo decoding process in this case. So if you stay in 150 milliseconds of delay in the delivery, you don't introduce further delivery in the process. So otherwise, we also tested that you can arrive even to maybe 4 milliseconds maximum, but you have to reduce the number. So you are not standard anymore, because you reduce the amount of turbo decoding steps that you can do. So you can still maintain in the stack the delivery time, but you will have higher error probability. Okay, with 150 milliseconds, you satisfy the standard.
There is another question, Fabrizio.
Yeah, there is. Please note what is the most authoritative reference for UAV-related communication parameters. I mean, if you mean transmit power, I think the reference is the local standards. So the countries, typically each government has its own regulation about the power that you can use in a specific bandwidth. In Europe, we have, for example, a regulation, a global regulation, but in some countries they use lower limits. So I think in terms of power, this is the most authoritative reference, is the body that assigns the spectrum, that licenses the spectrum. Even unlicensed spectrum have their own limits in the power. So you should look country by country somehow to get the correct data. For instead spectrum assignment and so on, again, probably the best is the body that assigns spectrum. Like, for example, in US, I think FCC is the one, because when they assign and they select the spectrum bandwidth for a specific application or a specific way of transmitting, they will specify the power, the roll-off, for example, the mask that your communication needs to satisfy. So unfortunately, that will be a problem in reality, because potentially country by country, we can have differences. Unless we use, for example, 5G, because if we all use 5G, the standard will be the source of information in that case. So I think there is another question that is split E latency is 10 milliseconds, but the hybrid RQ is still in the lower MAC. Can you? It's not very clear. What is the question?
Hello, am I audible?
Yes.
Thank you for a wonderful talk. Actually, I am Kirtan Gopal Panda from Indian Institute of Technology, Kharagpur, India. So my doubt is, in the split E, you mentioned that the latency will be 10 milliseconds, but still the hybrid ARQ will be in the lower MAC. Because of the hybrid ARQ, within 3 milliseconds, the user get the acknowledgement should be sent to the MAC. Otherwise, retransmission will occur. So because of that, the latency will be limited to 250 microseconds. I'm telling about the both, not one way. So 10 milliseconds, that's
probably
my
too
doubt.
much. Maybe it's a mistake. Yes, I will double check. Sorry, I didn't. I need to double check. But if you are aware about this, probably it's a wrong copy paste. So sorry about that.
And I have another doubt. Actually, right now I'm working in a standardization project. So we are also interested for standardization in IEEE. So for that, I have followed many of your mails also. So I will directly contact you later on that.
Yeah, that would be welcome. By the way, thanks a lot. Please feel free to reach me or Kamesh. We will be happy to work with you and to involve you in the operations. At the moment, there is still, a lot of space because we are, as Kamesh was saying, we are not in the preliminary, but in a stage that we are still collecting, let's say, data. So it's a good time to come to the meetings. We are not too much, let's say, in depth when it's very complex. Now we are stating up the scenarios and we are studying some channel models. So you are really welcome. Drop me an email. I will be happy to involve you in the next meetings. We are going to have a meeting, I think, next week. So if you contact me, we can already involve you.
Okay. Thank you. Thank you. I will definitely contact. And I am also working in this UAB based split options. So I will definitely go through your papers. You have recommended one paper. I will definitely go through that.
Sure. Yes, you are welcome. Let me know if you have any thoughts.
Thank you.
Thank you. And I see another question. What is the potential interference using 5G for UAV with flight operations near the airports? That's a tough question. To tell you the truth, for example, in Italy, the regulations forbid to fly drones near airports. So in this case, either you have an authorization, a special authorization, which is the same as you are flying an helicopter, for example, so very difficult to get for a drone. So typically, we don't have problems of interference because the drones are not allowed in the proximity of airports. They are, if it happened a few times to have a drone flying near the airport, typically they close operations while the drone is, let's say, either destroyed or sent away. Because it's not a problem, I think, of communication interference, but more of operational interference, because the drone is very dangerous if it goes against some flying objects. Then there is also a broad question that is, what is the biggest revolution you envision for drone communication in the next 5 to 10 years? That is very challenging. What I like, I mean, it's my personal opinion. I think one scenario is to integrate drones in networking. And I can explain you a few examples that I'm also trying to study. Because if we don't consider the drones only as clients of the mobile infrastructure, but with 5G, we can really integrate them because of the flexibility of the core, of the reprogrammability of the system. I think that one interesting thing would be an extension of this idea that now it's in this slide to split between some tasks between drones and maybe another part of the infrastructure, but also to use drones as, for example, Mac nodes. There is this concept of the edge computing, and drones, I think that they will become in the near future they will increase their lifespan, so they will be able to fly more time, because today they are limited. But I assume in 5-10 years, probably we will not have this kind of limitation, at least not so short flying time. But also a drone is quite a complex device, so it can also host services if we want. So we were studying, for example, the idea that drones become mobile nodes of the network that don't only provide connectivity, but also services to reduce, for example, the latency. And for situations in which you need fast deployment, this will become probably a game changing, because you could even not have any more in some parts the core of the mobile network, because you can replicate the core in a swarm of drones. So that, I think, will not be probably a visible sort of technology, besides the fact that maybe you see more drones flying around, but I think it would bring a revolutionary flexibility in new services, probably. So it might foster new capabilities and provide to the user much more advanced services. But it's my idea. I cannot look more in science fiction, you know. Of course, maybe we will have the smaller drones and also most invisible, but that I'm not sure on that. So I see another few questions. So could you mention the ability of Open RAN in BBU RRH separation? Also, what about the delay constraints due to blockchain security techniques? Okay, the Open RAN, I can use this maybe to explain the concept of Open RAN is that the way the protocol stack of the base station is sort of softwareized allows to detach the components. Okay, so for example, today in most cases we have something similar to the diagram on the top. So we have the radio unit where there is antenna, and the logic is mostly near to the base station. So the distributed and the centralized unit can be relatively near, or they can be detached, but with some limitation of the distance because of the throughput and the delay that you have. With Open RAN, the idea is that those interfaces, so the interfaces between radio unit and distributed unit and centralized unit are standard interfaces. So you don't need anymore a single vendor to build everything, but you can introduce other solutions. Like I was mentioning, for example, I can put a drone. If I know the protocol that connects the distributed unit to the base station, I can replicate it in the drone, and this will allow me to, for example, interact with the radio unit. So the main concept of Open RAN is to have this possibility to compose and recompose somehow the network. Of course, not runtime, but deployment by deployment. So you can exploit the Open RAN concept for a flexible deployment of the different functionalities. And this can be used to save power, you know, to, for example, avoid deploying maybe too much computation in areas that are not much, they don't require much coverage, but maybe just the antenna is enough. So there are a lot of trade-offs that you can exploit with the Open RAN. But the thing is, 5G provides some let's say, standardized interfaces. So if you maintain some of those splits that are in the standard, you have also a standard interface. So you can build your product or connect your product in a reliable manner within the end-to-end chain that can be provided by another vendor or another solution also. The blockchain, what about the delay constraints due to blockchain security techniques? And that is, I mean, if you want to employ blockchaining, you need, you will introduce further constraints in the delay and in where you do the processing. So you have to design either your blockchain software in order to be either distributed among or positioned strategically in one of the places in the Open RAN in order to satisfy your requirements. So it's let's say it's like somehow it's a loop. So you decide, for example, that you want to split in some way, then if you are using it, I see that you are thinking about blockchaining in the Mac. The Mac here in this diagram is where you have the UPF in orange. So basically, that is where you should deploy the Mac. So depending on where you put the UPF, that is basically the traffic steering module of 5G, you have to put the Mac and the blockchain in different places. Okay, I think I answered briefly, but most of the questions.
Right. So thank you very much for answering all these questions, Fabrizio. Obviously, the topic is quite interesting, and it's evolving right in front of us. So we are all the participants, if you are interested in joining us in the standardization effort, please reach out to Professor Fabrizio. The next talk is on August 7th. It is by Professor Metallock on reliability for advanced air mobility aviation communications. Professor Metallock is from University of South Carolina, and he's an expert in physical air. And I would like to, and I recommend all of you to join us again in the next month meeting on August 7th. So with that, thank you, Fabrizio, and thank you, Katie, for organizing, and thank you for all the attendees. We'll see you again next month.